So, a brief introduction to martingale theory. Once again, I keep it as short as possible. I just want to address the points which are later on necessary to remember, let's say, or to know when we go back to Black-Scholes. You can give a lecture, over one semester about martingale theory. That's a complete theory and a beautiful field in mathematics, which I cannot talk about here, obviously, in all the details. But we talked already about this idea of a martingale, and now I will give you a precise mathematical definition. And you will see that we need this definition. And I already mentioned in the fundamental theory of finance that basically is telling us if we have a martingale or a risk-neutral probability, well, then we know immediately there is no arbitrage. And in this case, pricing of financial assets, options, are easy to do. This is why martingales have such an importance in finance, because if we know there is a martingale in our financial model, then we know there is no arbitrage, which is a key assumption we assumed already and we discussed already. And then we know, well, if we have this, we can do pricing in a quite simple fashion. So what is a martingale? So let me define, so once again, definition of a martingale. A martingale xt, which is in the end, you see, a stochastic variable or process. A martingale xt has the following property. And the property is the following. If we build the expectation of the increment of this process based on the information of my filtration I know today S, so maybe I define, once again, T is greater than S. So S is what we know today, and then we go into the next day with T. So if I build the expectation of this increment, and this means based on my information, right? F is the set of the what we call a filtration, the set of event which we already know at period S, that is today. If we build such an expectation, then a martingale means this is 0, and that is equivalent, this is the same as if we build the expectation of xt based on what I know today, it's equal to the outcome of this variable today. Why is this the same? Well, if we take the expectation of this increment, right? I take the expectation of the first term, that is this, and then minus the expectation of my random variable given the information I have. Well, if I take expectation of an outcome today, that is what I already know. So xs has occurred. That is today. I see xs. And therefore, it's not necessary to build any expectation because I already see it in the market. So I can skip the expectation sign. And then you see here some minus. So if I bring this on the other side, it's here. And this is now telling us the idea of a martingale. The expectation of the future outcome, the future of my random variable in period t, based on what I know today, is the same as the outcome today. I give you I try to give you an idea. Suppose the stock market is a random process or is a random martingale. Suppose. I emphasize this. Suppose. Then this property would say, well, if I build expectation about the stock market in the next year, if t is the next year, then if this is a martingale, then my forecast is the price today. So if the stock market is today at 10,000, and someone is asking me, so what do you think is the stock market in a year? Well, then I build expectation about this random, this stochastic process, given all the information I have today, and if I know this is a martingale, then the best forecast you can do is to say, next year it's 10,000 again. If it is a martingale. That is what this is telling us. So the martingale property is just assuming or saying that the expected value of the future outcome is equal to the outcome of today. And this, you say, well, why should this be the case? Well, by the way, we also call this a naive forecast. That's, you would say, if you are a child, right? And if someone is asking what is the stock market and we have no idea, well, we say, well, maybe it's the same like today. So that's what we call the naive forecast. And interestingly, there is an empirical verification, not for the stock market, because I mentioned already that stock market are no good martingales. I will come back to this. But some of economic time series are really stochastic processes and are martingales. And there are empirical papers that studied thousands of these processes over now more than 50 years. And what they find, well, they looked at forecasts, naive forecasts, doing forecasts with this property, and then they used econometric models or economic models, right? Some economists build models to make better forecasts, to be better than the other one. And what turns out? Well, it turns out that all these models we have, they try to handle, for instance, exchange rates. Exchange rate is the typical example of a stochastic process. There are so many economic variables that have an impact on the level of the exchange rate that all models we have are not better than the naive forecast. The naive forecast is the best model today we have for forecasting an exchange rate. Whenever a bank has a model for an exchange rate, which they don't have, but they think maybe they have, they are not better than this. That is what we know from empirical studies. Yeah? So this is the best forecast you can do, and you beat all models if you handle. If the X is really a stochastic process, it's a martingale process. And by the way, for instance, even the central banks, the European Central Bank, and we talked a little bit about central bank policy also in my macroeconomics class, when they do forecasts, because they have to set the interest rate, right, to keep inflation in line with the mandate, which is below but close to 2%, well, they have to, in the medium term, they have to look what will be GDP, what will be prices in the future, and so on. They have to do forecasts. And whenever they do forecasts, they have a complex model. Millions is maybe too much, but thousands of equations. And for the exchange rate, what they are using, well, they use the same exchange rate today. If you watch the press conference of the Mario Draghi, when he's talking about the forecast, then he says, well, the assumption of our forecast is that the exchange rate is the same as today at 1, let's say, 10 or something like that. Yeah? This is an assumption even today central banks and other institutions use. It's a central point. Even it sounds simple and naive, but it's the best you can do if you deal with a martingale process, with a real stochastic process. Yeah?
Just give, apart from the exchange rate, a few more examples for like these processes.
I will come back to this because I already mentioned that stock markets are not, but I can show you that even stock markets are martingale because we can split up stock markets by the so-called Meyer decomposition into a trend component and into a martingale. And the trend, once again, is deterministic to forecast, easy. You already are able to do this. But there is also, in all the stock markets, a martingale process. So we can split it up by a decomposition, all the time series, into a trend component and a martingale process. And due to the fact that we can always do this mathematically, therefore we can handle all the time series which are not naturally martingales. We can transform these into martingales. And that is what we later on also do. Wait a second. So now, that brings me to a point that obviously we also have two different ideas. What we call a sub-martingale, sub-martingale, and the definition is follows: a sub-martingale XD has the following property, and now the property, so can I call this was the first one for a martingale. Now second, a sub-martingale has the following property. Well, we build the expectation over these two variables based on my filtration, but now I expect an increasing sequence, which is obviously equivalent to state that the future outcome of my random variable given my filtration is greater than what we have today. This is an increasing sequence. Maybe you see a stock market which is currently increasing, then you can say, well, that is not a martingale, right? But it's a sub-martingale. And if we have a decreasing sequence, we call this a super martingale. So super martingale, then same wording as above, has the property the expectation of this increment given the information of my filtration today is now less than 0, and that is equivalent to say that we build the expectations about the future outcome based on what I know today, but this is less than what we have today. So we have a declining trend. We call this a super martingale if there is an increasing trend in expectations, right? Not in level. So later on, I promise you, some of you are wondering and completely lost because you say, well, this means that the stock price should increase or decrease. No, it means the expected sequence is less than today. That does not necessarily mean that it's always going. In expectation, it goes down. But it could be that sometimes it's even higher than today. Yeah? So it's not one time point, it's the expectation of the future we built here on the left-hand side. And last week, we already learned how to compute the expectation, which is the integral from -infinity to +infinity, given we know the density function of the distribution of my random variable. Then we can compute this expected value. That is what we discussed last time. You see, all the things built step on step on the whole framework here. So, that is what you have to know, nothing else. Well, I told you there is more than that. We also have so-called semi-martingales and local martingales. I will not continue here in this direction. You just have to keep in mind what is a martingale and what is the property as I defined it. You have to distinguish a martingale from a sub-martingale, which is an increasing sequence in expectation, and a super martingale, which is an expectation value, a decreasing sequence. So these are the key properties you have to keep in mind. Yeah.
Just one question. In the lecture note, it's for sub-martingale and super martingale, it's with larger or equal to, or smaller or equal to.
Yeah, well, if we generalize this, we can. And the reason why it is better to write it with equal, because then we can say, if we have both, if a process X is a sub and a super martingale, well then it's a martingale, right? So if the expectation goes up and down, well then it's neither less nor greater, then obviously it's equal. Now that is the property or the idea we already used when we proved the put-call parity assumption. We have to show equality. We showed it's not less equal, it's not greater equal. But obviously, if it is this true and if this is true, well then it can only be if the equal, if this is equal, and therefore it's better to write less than equal and greater than equal. Yeah.
Well, question 5, the homework was, I think, about this as well. Will you talk about like today or next week, maybe?
Sorry.
It's about the 5th question of the homework we had to do last week because we had a negative martingale or whatever. Will you explain this stuff?
So now, before we go into the break, let me give one last example of this martingale issue before we continue. And the example is the following. Example. So suppose xt is a stochastic process. Xt is a stochastic process. It is independent over time. So it's independent. And mean is 0. Yeah, expectation is 0 of this stochastic process. So we have a stochastic process, xt, it's independent over time, and the mean, the expectation, is 0. And this is just an example you will also find in my lecture notes. There are more examples, but I will just give you here one to explain how to show that this is a martingale now. Now suppose there is a sequence, let's call it Sn, maybe a stock price. Yeah? You know, Sn starts at a first stock price at 0, maybe that is even 0, and then it continues with x1, x2, so it's a sequence until, plus xn. Yeah, so we have a sequence here. And then I shift this sequence 1 into the future, so Sn plus 1. Well, then this is gone, so that starts immediately at S1, yeah, and continues until xn plus xn plus 1. And now the question I'm interested in, well, is this difference of Sn plus 1 minus Sn, is this a martingale? Well, if this is a martingale, you know it should be equal to 0. Well, if I'm very precise, right, I have to say what is my benchmark time, and my benchmark time is here the information in my filtration until period n, right? Until this is what I have today, and then I have this tomorrow, this new event tomorrow, which I don't know. So obviously, if I plug in now here this sequence, and the beginning here is 0, you see this minus this cancels, this minus this cancels, this minus this cancels. So what remains here is then the expectation of the future event. If I subtract these two sequences, this Sn plus 1 with Sn, I have this. I assumed it's independent of time. That means that, well, you know, my filtration, that's basically property 4 to say, well, it does not matter what was going on in the past, so this information set is not relevant, and I assume that my process x has mean 0, and therefore, obviously, also my expectation of n plus 1 has then mean 0, and that is telling us immediately that this must be 0. So what we know then, that the increment, the difference of these two series are a martingale, because this is what we assumed as a property of a martingale. The difference over time, over these two xt minus xs, is equal to 0. That is the definition of a martingale. And so here we have defined that for a process which is independent, which has mean 0, which is following such a sequence, is really a martingale. You will find in my lecture notes a couple of examples also in relation already to finance, which are quite interesting to read, and I really recommend to take a close look to these other examples.